SIP9 Hub.
Hi there. Welcome to another episode of SIP9 Hub. For this video, we will be talking about antidifferentiation or indefinite integration. A warning though to our viewers or students, because you are assumed to have a background knowledge of differential calculus, which is an entire different course. Understanding the topics I'm about to present is primarily dependent on your understanding of differentiation, so that if you do not know yet what a derivative of a function is, I suggest that you go check these lessons first.
But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos.
Before we jump to our main lesson, let's try first to recall some of the most important procedures on computing for the derivative of a function, so that later on our work would be much easier. So I will not be presenting all, but I will only present to you what I think is most important. First on our list is the power rule for differentiation. So this is basically what we use when we are differentiating or taking the derivative of functions like this one. So you have x raised to n, you have a variable raised to a particular number, and to compute for the derivative of x raised to n, by the way, this symbol here is a symbol or a notation for the derivative. So we are trying to solve for the derivative of anything that looks like this, x raised to n. According to our rule, we simply bring down that number n, the exponent, the power, and make it as a coefficient, and then subtract 1 from that power. That's why it's n minus 1. Let's have a few examples. So we're going to compute for the derivative of this function. We have our function here, f of x equal to x cubed. And obviously, this is a variable raised to a number n. So the value of n here is 3. So according to the power rule, we will simply bring the power down as a coefficient. We will write that as a coefficient and then subtract 1 to that power. Let us try to do that. So let us write first the notation for derivative dx, the derivative of x cubed. By the way, this thing here tells us the variable that we are differentiating from. So we want the derivative of x cubed with respect to x. Okay, let us continue. According to the power rule, we bring down n, which is in this case 3, x, we follow the variable, and then subtract 1 from the exponent. So that is just 3 minus 1. So actually, we are done. The derivative of x cubed is 3x squared. So this is the derivative. This is the desired derivative. Derivative of y is equal to x cubed. Let us have another example. We have another function, f of w equal to w squared. Our function has a different independent variable, but that's okay. The power rule is still applicable. Our independent variable here is w. Computing now for the derivative, we proceed just the same like we did a while back. So the derivative of this time, our independent variable is w, so the derivative with respect to w of w squared. By the power rule, we bring down the exponent or the power, that is 2w, and then we less 1 from that exponent. So that's 2 minus 1. The final answer would be 2w. The derivative, this is the derivative of y equal to w squared. Let's have another rule. So that is your power rule. Let us proceed to another rule, that is the derivative of a constant. So this will review us on taking the derivative of a constant. So this is already the rule. The derivative of a constant, this is not a variable. This is just a notation for anything that is constant. C here is an arbitrary constant. And according to the rule, it is always 0. I mean, the derivative is always 0. Whatever constant is that, negative, positive, fraction, irrational, rational, as long as that is a real number, the derivative is 0. You have a function here, a constant function, f of x equal to 3. We do not have to think hard because the derivative of 3, since 3 is just a constant, is already 0. Another constant function, we have f of x equal to 1/2. The derivative of this is, again, 0, but let me write it properly. The derivative of 1/2 is, again, 0. How about this one? What is the derivative of this? We have a function, f of x equal to pi raised to e. Students, this is the wrong way to do it. I repeat, this is the wrong way to do it. If you're thinking this procedure, like you might write dx of pi raised to e is equal to, let me bring down e, make it as a coefficient of pi raised to e minus 1. If you're thinking this one, then you are absolutely wrong. Why? Because you are treating this one as x raised to n. That is not the same because pi raised to e is actually a constant. Pi is a constant. If you raise it to another constant, the result would be a constant. So the correct way of differentiating that one is to apply the rule for taking the derivative of a constant. We proceed d dx of pi raised to e is 0. This is the correct one. So do not get confused of the functions that you are differentiating. Let's have another rule. So for this rule, this is applicable if we are taking the derivative of a constant multiplied to a function. For example, you have here a function f of x equal to 5x cubed. And 5 is a factor, x cubed is another factor. According to the rule, we simply factor out c and then take the derivative of the remaining function. The derivative is, for this particular example, is what? Factor out 5 and then you only focus on the derivative of what is left inside, and that is x cubed. Well, for this derivative, we already answered that a while back. We know that the answer is, what was that? 3x squared. So that your final answer now would be 5 times 3 is 15x squared. This is your derivative. Let's have another example for this. You have f of q equal to negative 4q squared. You have a different independent variable again, it's q, but the application of that rule is still applicable. So you have the derivative of, what's this? Negative 4q squared with respect to q. So we write dq. The constant is negative 4, so we factor that out. And our main concern now is the derivative of q squared. For the derivative of q squared, we can apply the first rule, that's the power rule. So what is the power rule? We bring down, we bring down the exponent, that is 2, and then subtract 1 from the exponent. So 2 minus 1 is 1. So we do not have to write 1 as the exponent. That's understood to be 1. So now our final answer must be negative 8 q. The derivative of, so this is now the derivative of negative 4q squared. I hope you are able to follow. We have the last one before we proceed to antiderivatives. This rule is applicable when you are taking or computing the derivative of a sum or difference of two functions, and it's just telling us that the derivative of a sum and difference is equal to the sum and difference of the derivative of each function. So to get the derivative of a sum, we take the derivative of the individual function and then apply whatever operation is in between them. For example, we have a function here. We will treat this one as a single function and then another function. To take the derivative of that, our independent variable is x, so we write dx, x cubed, derivative of x cubed plus x squared. So let's present it. Let us apply clearly the rule here, but if you are able to master this one, there's no need actually to be writing it completely. You can proceed writing the answer directly. But for the meantime, let us write the solution completely. So that is the derivative of the first function, that's x cubed, plus, that's the operation between them, the derivative of the second function, which is x squared. For the two derivatives here, we are done with this. We know that the derivative of x cubed from the previous examples is 3x squared. So we use the power rule to compute that one. Same for the derivative of x squared. By applying the power rule, we arrived at an answer which is 2x. So the derivative of x cubed plus x squared is 3x squared plus 2x. Let's have another example. This time we have three functions. This is a function containing three terms, so we will treat each term here a single function. So we can extend that rule, the sum and difference rule. Let us now proceed computing for the derivative. So the derivative of 3, let me write it first. Let me write the function first. 3z raised to 4 plus 1/3 z squared minus z with respect to our independent variable z. Please be mindful of your notations that you use. It's not always x. dz. Okay, so how do we apply the rule, the sum difference rule for derivatives? This is the same as the derivative of the first term, which is 3z raised to 4 plus the derivative of the second term, which is 1/3 z squared minus the derivative of dz of z. I mean the derivative of z with respect to the variable z. So we are actually computing 3 derivatives. And there's no problem with this because we already mentioned some other rules to compute for the derivative. For example, for the first derivative, you have a constant. So what should we do with the constant? We factor out and then simply compute the derivative of what's left. So that is 3 times what? The derivative of z raised to 4. So can we answer it directly without writing everything? Z raised to 4, by applying the power formula, we bring down 4z and then subtract 1 to the exponent. We have 3. Plus, we do the same. 1/3 is still a constant. We can factor it out. So you have 1/3 outside and then multiply it to the derivative of z squared. From the previous example again, we know that the derivative of x squared is 2x. It follows the derivative of z squared is 2z minus the derivative of z. What is the derivative of z? Power rule. We can still use the power rule. Remember that the exponent of this is understood to be 1, so we bring down, this one. We bring down by applying the power rule. We bring down the exponent 1 z and then subtract 1 from the exponent 1. So what happens now? Okay, let us simplify. Three times 4, that gives you 12 z cubed plus 1/3 times 2, that is 2/3 z minus, what happens here? This is 0, right? 1 minus 1 is 0. And z raised to 0 is what? Is equal to 1. Remember, any number raised to 0 is equal to 1. Of course, the exemption is if z is equal to 0. So what's the answer here? 1 times 1, that is 1. The derivative of z is 1. So this is the collective derivative of the function. Alright, that ends our review on differentiation. Let us start now our main topic actually for this video, that is antiderivative. What is an antiderivative? But before we answer that question, let us first remember the process that we did under differentiation. Under differentiation, this is what we were doing. You are given a function. This is given. And your job is to compute for its corresponding derivative. So you are given a function. The result, after doing differentiation, is a derivative. For example, in the function y equal to x cubed, the corresponding derivative, as was presented a while back, is 3x squared. By the way, if you are confused, why are you seeing y prime here? Y prime is just another notation for derivative. So this is just the same. Y prime is another way of writing dx. Just an FYI. This is what we mean by differentiation. You are given a function, compute for the derivative. What about if you are asked to compute for the antiderivative of a function? So for example, we have a function, it's f of x equal to 3x squared. When someone asks, what is an antiderivative? What is an antiderivative? What does it mean? It means that we are looking not for a derivative, but we are looking for a function. We are still looking for a function. We are looking for a function. This is the problem, such that when we differentiate this function, so under differentiation, the result is 3x squared. Again, we are looking for a function. What we mean by an antiderivative is to look for a function so that when we differentiate that function, the result is 3x squared. 3x squared. And what is that function? This looks familiar, right? That is simply the derivative of the function we differentiated here. This means that the function that can give a derivative of 3x squared is x cubed. And x cubed is called or is considered an antiderivative for 3x squared. Let me put it in another way. When you are given a function and you are asked its antiderivative, you are actually treating this one here. You are treating that one as a derivative of some function. And that function is what we want to identify. So what is an antiderivative for the following function? F of w equal to 2w. So this problem, what is an antiderivative for the following function? This problem can be translated to what is a function when differentiated? The result is 2w. And this is again familiar, right? This is a derivative of the examples of the functions that we presented a while back. Let us try to go back. Where is that? Is it here? Yep. We can see here that it's 2w. This is 2w. This means that an antiderivative for 2w is w squared. Let us write that back. W squared is an antiderivative of f of w equal to 2w. Why? Why is that? Because when we take the derivative of w squared, the result is 2w. Another example, you have 15x squared. What is an antiderivative, or what is a function when differentiated? The result is 15x squared. Does it look familiar to you again? 15x squared? I believe that is a derivative of the functions we included under review of differentiation. Let us look for that. 15x squared. Here, 15x squared is the derivative of 5x cubed. Therefore, 5x cubed is an antiderivative of 15x squared. So simply write it again here. We have 5x cubed. So 5x cubed is an antiderivative of that function. Because, why again? Because when we take the derivative of 5x cubed, it would give us 15x squared. That simple. We have another function here. What is an antiderivative of the following function? We have f of q equal to negative 16q. What is a possible antiderivative for this one? Let us try negative 8q squared. Is this considered an antiderivative of negative 16q? To answer that, let us show first. We need to show. So this is yet a question mark. We need to show first let us show that the derivative of, so if this is to be an antiderivative, if we take the derivative, it should be negative 16q. If that happens, then we say that negative 8q squared is a correct antiderivative. So let's do that. Negative 8 negative 8q squared. The derivative has to be negative 16q. Alright, so how do we show this one? We need to take the derivative of this expression here. So what is the derivative? That's why I reviewed you on how to take the derivatives of functions. You have a constant, that's negative 8, so we bring it out. Negative 8 times the derivative of what's left inside, and that is q squared. The derivative of q squared can be computed by applying the power rule, and that would give us, if we do that, if we apply the power rule, that would give us 2q raised to 1, or simply 2q, and that is 16q. Yay! The answer is negative 16q, and that is the original question. What is an antiderivative of negative 16q? This means that, so what is our conclusion? What should be our conclusion? This means that negative 8q squared is indeed an antiderivative for the function there. So that is f of q equal to negative 16q. Okay, let us have another example of an antiderivative. We have a new function here. The antiderivative of f of x equal to 3x squared. This is familiar, right? 3x squared is familiar. That is the derivative of what? It's here. Where is that? 3x squared. Here. You have it here. 3x squared is the derivative of x cubed. Therefore, x cubed is an antiderivative of 3x squared. So we go back here. We know now that an antiderivative for 3x squared is x cubed. How about 2x? What is an antiderivative of 2x? An antiderivative of 2x is, well, this is 2w, it's not 2x, but we can actually adjust, we can pattern it here. The derivative of w squared is 2w. So that means also that the antiderivative for 2w is w squared. If we just change the variable into x, then an antiderivative for 2w or 2x is x squared. So this is an antiderivative. Antiderivative. Why again? Because the derivative of x cubed plus x squared is that question. Okay, I believe that is enough for us to clearly understand what we mean by an antiderivative. But wait, is that all? Is that everything with antiderivatives? The answer is no. My point is illustrated in the following question. Can we identify other antiderivative of the function below aside from x cubed? Because we identified already earlier in this presentation that an antiderivative for 3x squared is x cubed. But can we identify other antiderivative? This question means that it is possible that an antiderivative for a particular function is more than 1. Let's try to list the antiderivatives here. Here are the antiderivatives. One antiderivative is x cubed. Why again? Because when we differentiate x cubed, the result is 3x squared. But there are others. What do you think? If I write x cubed plus 1, surely x cubed plus 1 is different from x cubed. But when we differentiate x cubed plus 1, what is the answer? Derivative of x cubed is still 3x squared, and the derivative of 1 is a constant, and according to our rules previously presented, the derivative of any constant is 0. So this gives us a derivative of 3x squared still. This is the reason why x cubed plus 1 is still considered an antiderivative for 3x squared, because when we differentiate it, it still gives us 3x squared. Can you identify other function with the same derivative? So there are other antiderivative for sure. I can write x cubed minus 7. I can write x cubed plus 1/2. In other words, there are a lot of antiderivative. It's not just one, but there's actually infinitely many possible antiderivative for a given or for a particular function. In fact, to identify one here, I will simply write x cubed and add any constant. Because if I differentiate x cubed plus any kind or any constant, it would give you a derivative of 3x squared. So in general, we say that a family, so this is called a family of antiderivatives. a family of antiderivative can be written as x cubed plus c. Surely, we cannot write every constant that we can think of, like x cubed plus 1/2, x cubed minus 2, x cubed plus pi, x cubed minus e, and so on and so forth. So instead of doing that, we can generalize our answer, our antiderivatives. So when we see this expression is not referring to a single function, but it's referring to a family of function, because this is only representation of a lot of functions. Now, this process of looking for not a particular antiderivative, but looking for all possible antiderivative of a given function, we call that the family of antiderivatives. That process is what we call an antidifferentiation or indefinite integration. So antidifferentiation is just a term that is synonymous to indefinite integration. And when we say antidifferentiation, we are not only looking for a particular antiderivative, but we are looking for all possible antiderivatives. In the previous problems, we are, for example, this one, we are only looking for a particular antiderivative. One particular antiderivative for 3x squared is x cubed. But when the problem is on antidifferentiation, or when you are asked to do antidifferentiation, you are not only to look for a specific or a particular antiderivative, but to identify all possible antiderivatives. And to do that, because there are infinitely many possible antiderivative, we write it in a general way. So we add plus c. C here is an arbitrary constant. Notation, or what are our notations for anti-differentiation? Let's have this one. This symbol that we see here is our notation for anti-differentiation or indefinite integration. So when we see this one, this notation, beside a function, for example, 2w, this means that we are to look for that family of antiderivative for 2w. And that is done by identifying a particular antiderivative and then add plus c. Because again, antidifferentiation is a problem on solving or identifying all possible antiderivatives and not just one. Now, how about the other? Is that a factor? The other thing here that we see, dw. Let me write it here again. Let us write it bigger. 2w. That is the function that we want to anti-differentiate. But we see here another part, it's dw. Okay, this is just a notation. This is not 2w times d times w, but this is a single notation telling us that we are to anti-differentiate 2w with respect to variable w. So when I change the variable, say, what is the indefinite integral of 2x, then the notation that we attach to it is dx, when we mean we are to integrate this one with respect to variable x. When we have z cubed, when we are to anti-differentiate z cubed, then we have to attach the notation dz. This means that we are to integrate z cubed with respect to variable z. Because it is possible that we will be integrating or anti-differentiating a function containing a lot of variables. For example, x, y, z. You are to differentiate x, y, z. There's a lot of variables there, so if you do not put, or if you do not indicate which are treated variables here and which are not, then it would be confusing. So for example, if I write dx, this means that I have to integrate x, y, z with respect of the variable x. That means y and z will be initially treated as constant. So that is our notation for antidifferentiation. Let us erase this one. Let us try to give the answer for the integral of the indefinite integral of 2w dw. So again, what is this problem all about? We are trying to look for all possible antiderivative, hence this notation that we see here. So we read this one as indefinite integral of 2w dw. Now, how do we answer that? 2w, what is a function when taken its derivative is 2w? That is w squared, right? If you differentiate w squared, it is 2w. So we are right. W squared is an antiderivative. But wait, w squared is a particular antiderivative. And again, this problem is not all about looking for a particular antiderivative, but giving all antiderivative. And that is done by adding plus c. This means that any function of the form w squared plus c is an antiderivative of 2w. So some example, you might say w squared plus 1 is an antiderivative, a particular antiderivative. W squared minus 3 is a particular antiderivative. W squared minus 1/2 is a particular derivative, and so on and so forth. So it's really difficult to write it this way. That's why it would be better to write this way. It's shorter, but it includes everything that we mean. Another example, what is the indefinite integral of 3x squared plus 2x? That is already about antidifferentiation. The question is indefinite integration. So we are to look not for a particular antiderivative only, but to look for all possible antiderivative. And how do we do that? Well, for this particular function, the antiderivative for 3x squared is x cubed. Because again, when we differentiate x cubed, it gives us 3x squared. How about 2x? What is a particular derivative for 2x? It is x squared, right? X squared, because the derivative of x squared is 2x. But wait again, because x cubed plus x squared is just a particular antiderivative, this symbol is asking us to give us all the possible antiderivatives, and that is done by simply adding plus c. So this is a better way of writing it compared to listing all the possible antiderivative, and you will not be done till the end of time. Wow. Here is another example. Let's make it quick. Again, an antiderivative for 12z cubed is 3x raised to 4. An antiderivative for, what is that, 3 over 3? I think this should be 2/3. Let us change that as 2/3. An antiderivative for 2/3 z is 1/3 z squared minus an antiderivative for 1 is z. But then we need to add plus c because indefinite integration means looking for all or the family of all possible antiderivative for this one. Just notice this one, how we wrote dz. Since we are integrating a polynomial here, we enclose it first with a pair of parentheses before we attach dz. This means that we are to integrate with respect to variable z. And that's it for antidifferentiation or indefinite integration. As a summary, to do indefinite integration, we are to look for a particular antiderivative and then add c, because by doing so, we are actually giving a family of antiderivatives for the function. And that's what we mean by antidifferentiation or indefinite integration. Thank you for listening, and I will see you in the next video.